So let's talk about medium access control. We divide this medium access control in three different categories. Uh, and these are random access protocol, controlled access protocol, and channelization protocol. And we are going to look at these protocols in greater detail over this and the following lectures. Uh, so the goal of these protocols, for example, in the random access protocol is to reduce collision and manage retransmissions. And for controlled access protocol and channelization protocol is to avoid collisions. And specifically, the protocols that we are going to talk about include Aloha, CSMA, CD, and CSMA CA. For controlled access, reservation, polling, and token passing. And for channelization, FDMA, TDMA, and CDMA. So let's start with this discussion. So let's start by talking about random access protocol. So in random access protocols, devices can communicate without requiring any prior coordination. And one of the simplest random access protocol is something called Aloha. So the basic operation of the Aloha protocol is as follows. So when a node wants to transmit data, it will just simply send data without waiting for permission or checking for channel availability. Then it waits for acknowledgement. So if the node receives the acknowledgement within a specified duration of time, the transmission is considered to be successful. However, if no acknowledgement is received within this period of time, we assume that there was a collision and the transmission was lost, and the node will resend the data after a certain period of time. So what are the strengths of this protocol? That it has minimal overhead. So the protocol does not require complex coordination or channel management. So it's very simple to implement. The second is the low delay. So when a network load is light, the Aloha protocol can achieve very low delay as nodes can transmit data immediately without waiting for specific time slot or channel allocation. So in the context of Aloha protocol, a packet transmission has a window of vulnerability during which collisions can occur. And this window is equal to twice the on-air duration of the packet transmission. So there are two primary scenarios in which collisions can happen. First, during the packet transmission, if another node begins to transmit while the first packet is still being sent, a collision will occur and it can result to both of the packets being lost. The second is just before the packet transmission. If a concurrent transmission begins just before the packet is being sent, it may overlap with the first transmission, leading to collision and loss of both the packets. So one solution that has been proposed to tackle this problem is to introduce something called slotted Aloha protocol. So this protocol, as the name suggests, divides the time into synchronized slot, and this approach offers some key improvements. First, in slotted Aloha protocol, devices can transmit data whenever they have data to send, but they can only start transmitting at the beginning of the time slot. And these transmissions cannot be longer than the duration of the time slot itself. So what happens is that by restricting these transmissions to the beginning of time slot, slotted Aloha eliminates half of the possibilities that are there with the collisions. And a simultaneous transmission only occurs if they start at exactly the same time slot. However, because it has this notion of time, the slotted Aloha protocol introduces the need for additional synchronization. So all devices in the network must be somehow synchronized to have the same time slot and to ensure that the data is transmitted at the beginning of these slots. And this adds complexity to the protocol and may require a central coordinating node or other such synchronization mechanism. So what we find is that throughput of Aloha and slotted Aloha protocol can be understood and we can look at their efficiency. So when we talk about Aloha protocol, the maximum throughput that can be achieved is about 18.4%. What it means is that about 18.4% of the available channel capacity can be utilized for successful data transmission on an average, with the remaining capacity being wasted due to collisions or retransmission. In the case of slotted Aloha, in contrast, the maximum throughput that we can achieve is approximately 36.8%. So by dividing this time into synchronized slot, the slotted Aloha protocol effectively doubles the throughput when we compare it to the original Aloha protocol. And the increased throughput is due to reduced likelihood of collisions as the transmissions are now restricted to the beginning of the time slots. So next, let's talk about another random access protocol called Carrier Sense Multiple Access or CSMA. and it plays a very significant role in most modern wireless communication systems. So how does CSMA work? Um, it senses the carrier. So before transmitting, a device checks if there is a channel that is being used or it is idle. And if the channel is idle, that is, it is not being used, the device proceeds with its transmission and sends the data. And then it waits for some period of time to receive an acknowledgement. And if no acknowledgement is received, the device assumes that there was a collision and it prepares for retransmission. So the important question in the context of CSMA protocol is how should we retransmit once the channel or how should we transmit once it has been sensed that the channel is idle? Should we transmit immediately or should we wait for some period of time? So actually, if what we look at is that retransmitting immediately may not be the best approach, because it could actually lead to collision if the channel is still busy or if another device is attempting to transmit at the same time. So let's start now talking about specific variants of CSMA protocol that are commonly used in wireless networks. So first is CSMA CD. So CSMA CD stands for Carrier Send Multiple Access with Collision Detection. So it is a variant of CSMA protocol that incorporates, as the name suggests, collision detection, and it typically works on wired networks. So if you connect your laptop through an Ethernet through a wired medium, typically you are implementing CSMA CD as a collision mechanism. This mechanism is typically not used on wireless network because of two reasons. First, if you use the same antenna for transmission or reception, as is the case with the wireless device, it makes it difficult for us to simultaneously transmit and listen for potential collisions when the transmissions are happening. The second is that during transmission, the strength of the transmitted signal is much higher than the incoming signal that is arriving at the antenna. And this disparity can drown out the received signal, and it makes it almost impossible for us to detect collision while we are actively transmitting. And this makes it very difficult to implement a mechanism such as CSMA CD at the transmitter. And due to these challenges, CSMA CD is not a very practical solution for wireless communication systems. Instead, we rely on something called CSMA CA, which is Carrier Sense Multiple Access with Collision Avoidance. So what is CSMA CA? So it is a medium access mechanism that reduces the probability of collisions that happens on a wireless channel. So let's look at briefly how CSMA CA works. So before transmission, a node checks if the channel is clear by sensing the carrier. So if the channel is clear, the node defers the transmission for some random interval to minimize the likelihood of collision. And then it selects a random interval, and the random interval is selected maybe by a uniform distribution between 0 and a maximum window size. And it sort of like then uses this maximum window size to sort of like defer the transmission to occur at this particular period of time. So why is choosing an appropriate window size crucial for efficiency of CSMA-CA mechanism? Because if the value of W is large, it minimizes the collision, but it can lead to underutilization of the channel, and it can lead to excessive weighting and vice versa. So let's look at this aspect in a bit more detail. So how should we choose the window size? Should we make W to be constant? Maybe that's not a good idea, because if the traffic load varies, it might mean that your network doesn't adapt. So what should be the value? If there is less chance of collision, we should try to keep W to be small. Otherwise, we should increase the value. And the reason is that if the value of W is small, then you are better utilizing the channel, but you are increasing the probability of collision. Typically, when we talk about these wireless networks, the value of W is chosen according to the binary exponential backoff algorithm, and we set the slot time to be 2 times the maximum propagation delay of the channel. If, for example, if this is the first transmission, we send it immediately. However, if there is a collision, say after the ith packet being transmitted, we pick W randomly from 0 to 2 to the power I minus 1 time slots. So what are the various trade-offs that are made in this algorithm? A more aggressive, that is smaller window size, may lead to more collision but higher channel utilization. On the other hand, a smaller window size would cause lower channel utilization but less collision. Hence, the trade-off that we are typically looking at is the channel utilization versus delay. So the right value depends on the kind of application that you want to have and the traffic load and the number of stations or nodes that are contending in the network. So this was actually CSMA CA protocol. Next, now let's talk briefly about a problem of sharing spectrum with different devices contending for the medium. Let's first talk about something which is called hidden terminal problem. So what is hidden terminal? So let's look at this figure. So we have three devices, device A, C, and B, and device A and B both want to communicate to device C. If we let's say that the device A is transmitting to device C, what happens is that the device B cannot listen to device A's transmission, and thus it doesn't know if device A is transmitting. So what can happen is that device A starts transmitting to device C, and since device B cannot hear device A, it also starts transmitting to device C. And of course, this is not something we want, because if two devices are transmitting at the same time to device C, their transmissions will collide at device C, and it will cause interference and it will cause packets to be lost. And this is called hidden terminal problem. And this is a problem that we would like to avoid. So what could be a potential solution to this hidden terminal problem? One common solution that is employed is that when the channel is idle, the transmitter can send a short message, which is called request to send. Then the receiver or the device C in the previous slide will actually send a CTS, and it will only send the CTS to one node, which is then allowed to transmit. And the other node would receive the CTS and know that, okay, there is an ongoing transmission, and it will actually not transmit to the node C. Secondly, there is a chance that the RTS message can collide, but since RTS messages are so short, their collisions are less wasteful, and that sort of like doesn't cause as major issue as like your data packets with getting collided. However, there is an overhead for you to send RTS CTS, and this can actually lead to poor channel utilization, especially when the contention is low in the network. So let's look at the hidden terminal and the RTS CTS in action. So let's say we have node A, it sends an RTS to node B, and then node B sends a CTS, but this CTS is also actually heard by the node or the computer C. And this actually means that the device C actually doesn't communicate when the node A and B are communicating, because this CTS that node it heard from node B actually meant that the node C would actually wait for that duration of time before it actually starts sending traffic to node B again. And this actually allows you to avoid this hidden terminal problem. So with this, we come to an end of this lecture.